Okay. Hello, everyone. Today the talk will be about quasi-triangular and quasi-Hopf algebras. And basically we'll see the axioms, the definition of these algebras and their representations as, and how they come from monoidal categories. The motivation is that if we have a monoidal structure and a monoidal category, we want to see what it gives us back in algebras, in bi-algebras. So at first we will see I will begin from the fact that for every monoidal structure we get back a quasi-bi-algebra. So we'll begin backwards instead of defining the quasi-bi-algebra first and then showing that it has a monoidal structure. Then I will do it differently so that we can see why we need a quasi-bi-algebra to get a monoidal structure. So we let A be an associative algebra. And we have also delta co-multiplication map, epsilon a co-unit, such that the morphism of algebras satisfying this relation if we consider now as rep A the category of A modules with tensor product, and unit as follows. An element of the algebra acts on the tensor product via co-multiplication. And and the co-unit acts like that. Then we have that any monoidal structure of the category of A modules defines a quasi-bi-algebra structure on A. Here A is only an algebra, not a bi-algebra. We just have a co-multiplication and co-unit map, but they satisfy only this. We will see that we need to expand to generalize a co-associativity axiom to get what we need. So, okay. Before proving, I will give the definition of the quasi-bi-algebra so that you can see the axioms that we need. Yes. We let again A be an associative algebra. Again, we have the co-multiplication co-unit map satisfying this relation. we let phi be an invertible element in A tensor A tensor A. Then we say that A is a quasi bialgebra. If first phi satisfies a pentagon relation, two, delta is quasi-associative and quasi-co-associative. And third, we have that phi satisfies a co-unit axiom. In the case that we have phi equals 1, that means that we have a regular bialgebra and not a quasi-bialgebra.
Sorry, phi means where?
A tensor A tensor A.
What does it mean? Could you repeat?
Sorry? Where phi lives. Phi lives in A tensor A tensor A. Not exactly here. It's like like you add. Yes, sorry. He asked what is phi 1, 2, 3, 4. We imagine I acting on, let's say, something like that. Like the R matrix in quasi-Hopf algebras, for example.
Right. So this 1, 1, 1, that we don't put in. Or rather, leaving 8 and 8 and 8 and 8. You can also do it this way. So,
Yes.
So you just add a 1 in the middle in the thing which is missing, right? Or
Yes, exactly. Like the R matrix, it's the same.
yeah, but maybe you can explain us in detail because we don't know R matrix.
Okay. So, for example, if we have something like that, we mean this thing. By acting by this dot, we mean that we take, we write it as like that. So we take phi of 1a, phi 2b, etc. And in the case that it is something like 2, 3, something is missing in the middle, then you just don't put nothing on that position.
And what is the last thing? The phi 3 of CD? That's what you find out, right? I'm not sure. No, because I thought that phi is an element of 8 and 8 and 6, so it's a tensor product of phi 1, phi 2, and phi 3.
Yeah, in that case, I think that this is a co-multiplication. I mean, like
Okay.
Here. Sorry? Here.
That's what
Yes.
you mean to do that. It takes phi 3, applies the coproduct, gets 2 elements, and then multiplies
Yes,
That's
I think.
a different thing from multiplying CD with the algebra structure.
And then, yeah, right. So I don't know.
Let me see something.
I think it should be with the algebra structure because on the right hand side of the pentagon relation, phi could be 4, maybe a. Yeah, they all need.
No, they all need the fourth quantum power.
So this is a relation of 4 times.
Yeah.
Then okay.
Well, maybe we can understand it through the proof at some point, because we will derive, I mean, the whole point was to derive the axioms from the axioms of the monoidal category. So at some point, this will be clear by itself.
Okay, yes, I will give again the pentagon relation and we can see. Yes, okay. So the proof of the proposition. I will begin from the pentagon relation so that we can see what's happening. So, okay, so in order to have this pentagon relation to be satisfied, we have to find a map that satisfies it. And we take as a map we define an associator via the element phi. We let phi act on this tensor product.
Are you assuming now that you have an algebra and phi?
Yes, monoidal structure. And we find phi out of, I mean,
Yes, sorry, I have. Yes, sorry, I was confused. Yes, basically we have an associator, that map. Let's say that we have an associator. Then we define phi as that element. So in that case, if we take the maps, we get the same pentagon relation due to the fact they interchange the same indices, let's say, on the.
So there you complete, for the first thing there, you have reciprocity, so tensor D, right?
Yes, here it's. So in that case, this map is corresponds to phi 1, 2, 3 in that case. This map corresponds to this element here, and yes, this is how the pentagon relation is satisfied.
But what is the element then? Phi 1, 2, 3, 4?
I understand it, for example, here as, yes, I understand it as something like that here, for example, where we leave we have here B tensor C and we leave it, we don't change the parenthesis. Let's say here, I understood it as phi to act going in here as
So you say that on 2, 3 you add the identity, right?
no, that I'm putting here phi 2, phi with index 2, the second position of phi.
But you are basically saying that for a phi A, B tens C tens D in this map, you associate an element in A tens A tens A tens B, 4 power of A, right?
Yes.
So which is this element? Because here you just define what is the original phi in A tens A tens A. But then it seems that out of this phi, we can associate an element in A to the power 4, right?
Yes, basically when I was doing the proof, I understood that I'm putting this thing here and I'm acting via the coproduct. And
Yeah, let's move on.
yes.
We talked about like phi sub 1, phi sub 2 stuff. So are you assuming that phi is like a simple?
This is sweeter location, we ignore the sum.
If it's 1, 2, 4, then it's like that you put 1 in the third position and identity. But here it also exists that thing that's like 1, 2, 3, 4. Sorry? Oh, yes. Okay.
So the one behind, put it up.
The product is an algebra map, and that's what we can use.
Oops.
We say
Yes.
what's the phi of algebra,
Yes.
then what's the dot of what kind of code?
What's the data? The associative algebra A. Okay, the multiplication, the unit, of course, from the algebra structure. And then these two maps, delta and epsilon, which are like coproduct and co-unit, but without co-associativity, but with quasi. And the phi, of course, is the data.
For all invertible, it's one phi.
It's 1 phi.
It's one phi, okay.
Yes. Yes.
Two requests actually. First, in 3, so you put in a 3 tensor and I think it does a 2 tensor and on the other side there is a 1.
Yes.
So you use multiplication for it. And second request, repeat my question for the mic.
It's not.
Repeat my question.
Okay, if I use multiplication for the co-unit axiom, no, it's like acting every element, every position in. Let me write it. that thing. Alpha 1, beta 1, and A1, D1.
So the one on the right hand
And
side
basically
is
the-
one tensor one.
There.
On the right hand side is one.
Okay, basically it's one, yes, it's one tensor 1, formally. Basically there one, sorry. By writing this, basically instead of 1, I mean the identity map.
Yeah, yeah. On the left hand side, one is identical. On the right, one is what?
3 tensors. 1 tensor 1, tensor 1.
So that's a one in the middle. So you have to equal to, right?
Sorry, if?
What have you written here?
That I didn't know, I thought that he was confused because I wrote 1 as a map there. And I was just writing id.
Just to put the phi at the end. Just rewrite. There's a phi missing correctly, right? Or
Sorry, if?
phi is missing here.
Yes, I just wrote it informally, let's say, so that
Okay, but phi is a three tensor. You put it inside, you get identity,
identity.
you get the k element. So you should get a two tensor.
So in this third axiom,
We will see it now.
Okay, good.
Okay, you meant how it is proved, I think. Yes,
Yeah,
okay.
no, really what it means. I'm confused about it.
This thing comes basically from the left and right, maps that we have.
what he's asking is this equation that you've written up here for the third axiom.
Yes.
Means the right hand side should be 1 tensor 1.
The one of the algebra.
Okay. You mean that I have to write it like that?
Yeah, but the thing is, it's not a 3 tensor, it's a 2 tensor because when you have the epsilon, you get rid of 1 tensor, right?
Yes.
Okay.
Yes,
so-
okay.
So in this case, it's just like,
Yes.
Okay.
Okay, now let's see how we can derive the quasi-coassociativity. We need the associator to be a linear map. So if we take this, from that we have this equality here.
so that is by definition of the phi on the right.
This is the definition of the phi, and this is how A acts on that. Because I consider it as that's why I'm using delta cross 1 here. And now we will do the other way, and we'll consider it the other way so that we can derive the coassociativity axiom. So again, here we have the definition. And for these two equalities to be, for these two terms to be equal, we have the coassociativity axiom. For the elements in the algebra. Now we have to also, for the co-unit axiom, what needs to be done is to show that the triangle relation is holds. One moment so that I can use the same notation. Yes. So we know that in the category this holds, and whoa. And now we'll use this so that we can derive from that the co-unit axiom. If we begin from the right, here we'll use a definition of phi. Then we can write k as a co-unit of k, because the co-unit at 1 is 1, and the co-unit is a morphism, as we have supposed. Yep, okay. Now we let phi act, and we have again that epsilon is a morphism. And this term must be equal to that term. So from here, we have again the co-unit axiom. Or, yeah, here formally. A. K, an element in the ground field of the algebra. So that's why I can use like that a co-unit with K. Okay, we have the triangle relation that holds in the category. So I'm taking that and then that and see, and we have two results and they have to be equal. From that map, I have this. From the right map. Via the definition of the right map. And then from the left map, from this side here, I'm taking the left identical as the left map and then phi on that element. I use a definition of phi here. Then K is an element in the ground field. So I can write it as epsilon of K. Also, epsilon, we have supposed that it is a morphism. So, sorry, first I act phi in here, and then I put it into the co-unit because its co-unit is a morphism. And then I write this element as identity cross epsilon cross identity acting on that. And then I use again the definition of the associator, and this thing must be the identity because we don't have it here. These two must be equal because it's that and that.
Exploding.
Yes. Okay, now we also have the opposite proposition that a quasi-bialgebra gives a structure in the monoidal category, in the category of A modules. So we let A be a quasi-bialgebra. Then we have that the category rep A of A modules. Equipped with a tensor product and a unit object K and we let the co-unit act like that. And with the associativity morphism, such that we let phi act on that. Yes. Is a monoidal category. The proof is similar to the previous one, so I think that we can skip it. It's just calculations, but if you want, I can do them. But it's the same thing, I mean, in the opposite way. The only difference is that you have to consider elements of the modules and not only of the algebra when doing the calculations. The only difference is that we take elements of the modules, such like that, and not only specific in the algebra. In the previous proposition, because we were going the other way, I was using, for example, phi A field A. But it's the same technique. As a remark, if phi is 1, then we have a bialgebra. And in that case, we'd get a strict monoidal category.
But here you can really answer the question if you define of X, Y, Z, W.
Here.
Yeah, if you have 4 guys and you have a 2 that you consider as a single guy.
Okay. For example, if I had something like that,
Yeah.
And we were writing, okay, one. Okay, in that case, it's easy because we consider. No, here it's 1,3,4. 2 is missing. So we just do that. But on the other, there was also another notation which was like that.
Can you recall the difference between the strict monoidal category and monoidal category?
Yes, in a strict monoidal category, basically we consider tensor products like that are really equal, not only isomorphic. So when we set the associator to B1, basically we say that these two things are the same thing. When a category is not strict, and we use an associator which, for example, sends X, Y, Z to something else here, they are isomorphic, but not in a canonical, let's say, way.
Is it related with what we saw last time? So last time we had what? Associators. So
No, it was a general one.
non-strict monoidal.
It was non-strict. I'm just saying as a remark that if we take a bialgebra and we want to find the structure that we have in the representation category, it's a strict monoidal category. And sometimes we need the weak monoidal category so that we can have more structure instead of restricting to the strict case.
Right.
And yes, here I understood that as that I can act this via the coproduct. Okay, so it was just confusion. Okay. Okay, now we will, there's also a proposition that says that if we have two quasi-algebras that are equivalent, then the monoidal categories are equivalent. But before going into that, I have to give a definition of tensor factors. So, definition. We take C and C prime to monoidal categories. And a functor between them. Yes. And we say that an isomorphism of functors yes. Okay. Is called a tensor structure on F. If the following diagram commutes. Yeah, it won't fit.
It's an isomorphism of bifunctors. Because
Yeah, yes.
so the bifunctors, they are tens composed with FF and F composed with tens.
Sorry, F composed with?
The left and right hand side are bifunctors.
Yes. Okay, I will erase that because the diagram can't fit in there. It's called the tension structure on F if.
Yeah, but
Yes.
before what it's called it's a binatural transformation. It means that if you fix one of the two variables, it's a natural transformation.
Mhm.
Okay. It's a natural transformation as a whole.
Okay, let me do.
To start with this model,
It's F is just a factor from the first category, the second one.
so it does to map tensor to tensor. Okay, so it can be.
Okay, can we leave it here like that?
Yes, yes, sorry. Okay, so.
So sorry, I still don't get it. So where is the dot? There should be a dot, right?
A dot?
Yeah.
In F, and there are two dots in there. You mean,
The sentence. So you suppose that you have C prime two monoidal categories, and F something, and then you have J, and you define F or you define J? No, we suppose we have J.
No, sorry. Yes. Let me fix it. Oops. So we suppose that we have two categories and a factor between them. And then we say,
So the dot is at first C prime. So and F. And
Yes.
That's a functor.
and then, yes, it's a factor. And then we say that an isomorphism J is called the tensor structure. Here's a dot. I mean,
Okay.
here as phi, I mean the associator, not the previous phi as defined, just the general associator or the monoidal category.
So do you have an example? Just to...
Basically, we will see now the proof that we will use that so that we can solve that if we have two equivalent quasi-bialgebras, then we get two equivalent monoidal structures.
Yeah, but who would be C and C prime in this case, just to have an idea?
In that case, if we have an algebra A and A prime, we take the monoidal category of the A module category of each one. So A mod and A prime mod, let's say, and the factor between them. And they have to satisfy this. And because of the fact that we have a monoidal category, we have that the unit object of the first monoidal category must be mapped via F to the second unit, to the unit object of the second category, and this relation about the J-map and the unit object, where X is a general object in the category.
So you don't assume that F preserves the monoidal structures, basically?
No, basically it's a definition, let's say, that it does now.
So F is just a function of categories.
Yes,
Monoidal.
basically if we remove these two, this thing can be defined in for semi-group categories in general. These two relations are specific for the monoidal categories. I just use it in one definition because we work here with monoidal categories only. Yeah.
Is this the same thing as a lax monoidal functor?
As a?
Lax monoidal functor?
I don't know it.
So what is something which on the nose says f x times y is f of x times f of y? Is that the name to right? Okay, so that's monoidal functor. Okay. Yeah. So the nuance is a strict monoidal functor mix, and that's good.
Okay, yeah, no, but the other name. So proposition. Yes. First, I will define what it means that two quasi-bialgebras are equivalent. Let A and A prime be two quasi-bialgebras. Then we say that an equivalence between them is a pair of theta and J, where theta is an algebra isomorphism. And J in A prime cross A prime is an invertible element. Such that? Yes. I will keep the diagram for now. We have this relation for the two co-multiplications. For the associators, this relation must hold, and this one about the co-unit and the twist. J is also called a twist.
Shouldn't be another theta or theta inverse because
Where?
for the definition for the delta prime, you apply two elements in A prime, right?
Yes, but we have an isomorphism. Theta is an isomorphism between A and A prime.
Yeah, but it's still like isomorphism, right?
Yes.
So here you apply theta after applying delta, so I guess you have also to apply theta inverse before applying delta, otherwise it makes no sense, right? Or
Yes, okay. When I was reading this, I was thinking about that we apply somewhere here theta inverse, that we have to get them back. So
no, but there's only one this time.
yes, exactly. So this is in A. Yes, I think it's okay. So now I'm going to prove the proposition that if two quasi-bialgebras differ by twists and they have equivalent monoidal categories, do you need this or can I erase it? Okay.
I guess for the second one also there should be some theta, right? Because the phi prime lives in A prime to the power of third, and on the right you multiply j's, but the j's they are in A prime times A prime, so they should be phi prime, not A prime.
Yes.
You have to apply phi theta
Here.
theta to the truth. I think on the left of phi, right?
Like the phi is a map for the algebra A. Here we have elements in, so we have to put here, I think.
No, on the left, because phi, if you do phi as an element, it's not a map, right? Here it's
Yes, it's an element, but it's an element of A. And these are in A prime.
yeah, so basically you have to sum these three powers of A into A prime. So I think you have to put on the left theta.
Ah, not inverse. Okay. Yes. Okay, so proof. Theta is an isomorphism of two algebras. It uses equivalence of categories. And we define J, the map J that we had. Yes, so it's erased that we have the statement that two quasi-bialgebras, if they are equivalent, then their monoidal categories are equivalent. So we define this function J as the element J acting on the tensor product of X and Y. It's one direction. Yes, it's one direction.
Sorry, I didn't sleep well last night. So how do you define F starting from theta? That's not looking for you, or?
Here, yes, I define F via theta.
You tell us, or it's implicit?
Basically, since we have an A module here, and every element on that we have of A, we send it to theta A, since we have an isomorphism between them,
Because
and
it's
extending by
the
linearity on modules. That's it. And yes, now if I take this map and we put it up there in the diagram, we can see that it holds and okay, specifically, if by using the definition of this map and this relation here, because we have it there and there, we can see that the diagram commutes. But yeah, do you want to do it? I think. Okay. Now the next part is about speaking about the quasi-triangular structure on bialgebras or quasi-bialgebras, and basically we will see that a quasi-triangular structure gives us a braided monoidal category in the presentation in the A module category. So at first I will begin with the motivation behind the braided monoidal categories. Basically, in the braided monoidal categories, we want, let's say, to distinguish objects like that. In the monoidal categories, objects like that are, we have, if I take a map, basically we'll have that if we take it twice and applying it again here, X, again here it will be the identity. In the braided monoidal categories, we want to get rid of this restriction and generally to have, so that we have a map that this is something else. And this comes from, basically that is called braided because of the braid group where something like that is not the identity. And in that case, basically, okay, we will basically in that case we will see later, but so that we can define a functor like this in the A mod category, we will need an element R in A cross A. Where delta op is a common duplication doing it in the opposite way, in the opposite algebra, let's say. And yes. But what would be?
What would be then beta xy in that case?
Acting or with R on the, I think acting with R on the tensor product, on an element of the tensor product. Yes, I think, yes. But if we want to define this map, we have to also we need a new relation, which is called hexagon relation, to be to hold, so that everything is defined correctly. And this basically comes from the braid groups. So let me write a diagram.
And do you know to what it corresponds in pictures?
Yes, basically, for if we have a general braid, we color the strands with some vector spaces, and we consider the whole braid as a map from some vector space to another vector space.
No, I understand, but rather the question for the braid relation, because in terms to see where it comes from.
Yes, I will draw also the braid, let's say. If you,
do it before, so that when you see
it's basically the same diagram, so it's not something like an isotopy or a Demassier move. So I will do it like that.
What's the
Sorry,
delta?
opposite. Doing the map, but reversing the elements, like the opposite multiplication. Exactly. It's the same thing.
delta composite. No, but not this beta. It's just if you write delta A in Twitter notation.
Yes.
Maybe,
Okay. Generally, we can write A as this thing. So delta op will be this. That's all. It's just the same thing with the opposite multiplication in algebra. Oops. Okay, so this is hexagon relation, and so that we can see it in braid diagram. This thing in braids doesn't mean something specific. It's just that we don't change the orders of the vector spaces. Imagine that we have three strands colored with V1, V2, V3. This thing here means that we exchange the V2 cross V3 with V1. So it's something like that. Imagine V2 cross V3 as one element. And then again, nothing, we just use the associator here. And if we go this way, it's just that we exchange V1 and V2 at first. Then the associator, which is nothing geometrically here in the braid group. And at last, we exchange 1 and 3. But 1 is this strand, so basically these two diagrams are the same thing. It's just that if you take two vector spaces and exchange it with 1, it's the same thing if you exchange the first with the second and then the first with the third. And yes, this can also be extended in many vector spaces, but the list that we need is this, and then we can extend it, of course. So we'll give the formal definition of the braided monoidal category. So definition, a braided, oops, sorry. monoidal category. Is a monoidal category C. Equipped with an isomorphism of bifunctors beta such that the hexagon relation is satisfied. Two, the hexagon relation again is satisfied, but with beta inverse instead of beta. And three, we have that beta x comma the unit object is the same with beta unit object comma x, which is identity. The second relation means that in the braid group diagrammatically means that we can also take the other type of crossings. If we beta one is a means that we take the other type, the negative crossing.
Okay, after identifying x as the I using the monoid.
Yes, the unit. Yes, I is a unit object in the monoidal category C. And we can also extend the definition of the tensor factor that we saw before with a braided tensor factor. So a braided tensor factor between two categories C and C prime, which are braided monoidal categories. Is a tensor factor making the following diagram commutative. So we also have to impose this diagram so that it respects them with a braided monoidal structure. Yes, now I will define the quasi-triangular structure. Test.
Why the -1? I guess also the lower horizontal.
J before was a factor from this to this. So it's the inverse of it. That's it. Now, the lower one. Yes, the lower one must be J. Yeah, I think that if you just reverse the arrows, it's the same thing. It doesn't really matter. With removing the inverse, of course. Okay, first I will define the quasi-Hopf algebra, and then we will define the quasi-triangular structure for the quasi-Hopf algebra, and we will see that it can also be reduced to a version of for Hopf algebras. If we set phi equals 1, for example, then okay, so we have a quasi-Hopf algebra. Is an associative algebra of a K. With two homomorphisms, the co-unit and the co-product, and an invertible element phi such that it satisfies a condition of a quasi by algebra which is how phi, which are relations between that we saw between phi, epsilon, and delta, and additionally, A is also equipped with an anti-homomorphism S, and alpha and beta, two elements in A, such that yes. Three. I will give later what all these prime and etc. are. Here, epsilon alpha. Oh, no, here it's alpha, here it's, no, here it's A, here it's alpha. Alpha, A beta. I will, what do you mean?
I mean that it seems that what you put inside of the epsilon here is the thing which twists somehow down to pods, so it should be also the same thing at the lowest or the beta. I mean, it doesn't coherent to like But later you can motivate where it comes from.
Yes, basically.
So that will be
Okay. So, and here we write these three elements using this notation. So this is what AR and phi of S and phi T are.
Could you recall the non-quasi version of that?
Basically, it's the same if we put alpha and beta equals 1 and S, the usual antipode.
Yeah, but what did you get on the right? You get epsilon of R times the unit, right?
You mean here?
Yeah.
Okay, here to this will be 1.
Yeah.
1, 1. So it will be beta equals.
No, it would be 1 on the beta would be 1, right?
Yes. Okay. No, this is 1.
What would
This would stay. Sorry, this is not. Okay.
So this makes sense. And up there, I think it's rather epsilon of A times alpha, right?
Yes, sorry. Sorry. Yes, sometimes I write them too similar and I cannot distinguish. Sorry about the typo. Yes. Okay. And now a definition about quasi-triangular.
So maybe just for the non-quasi case and for the group G. For the group G, you know what it is? It's G and G inverse equals 1. Yeah. And so how do you get that? You have G, in G the product is G times G, and you apply S, which is inverse, and you have G inverse times G, and then you multiply with 1. So that's if you have alpha equals 1 up there on the first line, and A equals G, and A prime is equal G, you will get that G inverse G equals 1.
Could you repeat this in the microphone?
Or maybe,
Yes.
So I'm just recalling I'm not sure if we saw it last time, but so I'm just saying that. So in the non-quasi case, just for Hopf algebra and in an example, so for G, for K of G. So the group algebra. For that, a basis of elements was elements of G, and the co-product of G was G times G. Okay, so in a sense, G in this notation here, I want to understand what is this thing. Sum over R of SAR alpha A prime R. This in our case, alpha equals 1, A prime equals G, S of AR is S of G, and S of G is G inverse because the antipode there is G inverse. So this is basically G inverse times G. Because here implicitly you have the multiplication, right?
Yes.
Yeah, it's not written, but you use the multiplication of the algebra. So here we have multiplication, and this is 1. But what is 1? It's epsilon of G times 1. Because what was epsilon? Epsilon was taking any guy to 1, right? So this is what happens. This equation, in case of alpha equals 1, is what is written here. So it's really the fact of having an inverse. And somehow you have to twist it, and that's what he will explain, why there's an alpha which enters the game. This I don't know. He will explain us.
What's the motivation for quasi-function?
Well, you
Before German gets a
Right.
Yeah.
Because if you deform Hopf, you stay.
yes. You get something quasi-isomorphic in the case of semi-simple Lie groups or Lie algebras. So if you want to quantize semi-simple Lie algebras, you have to deform in a more flexible space. Yes.
First, the question is, there must be something different from Hopf algebra to quasi-Hopf algebra. And second, repeat the question.
First, repeat the question. I didn't get it, and then I will repeat it.
Okay, the question is, what's the difference between this quasi-Hopf structure and the Hopf algebra?
Oh, so well, in a quasi.
Because you make this example, and I don't really see the difference.
Well, the difference is that here I don't have alpha. There's no alpha. Alpha equals 1. And beta equals 1, and there's no phi. Phi equals 1, and and that's it. But he said beta equals 1. It's not the same beta. Sorry.
In the third formula here, so right next to the S equation, that'd be a beta between the phi S prime and the S phi double prime.
Here?
Yeah, that'd be beta.
I have no idea. Oh, because you say there are 2 here, there should be 2. Yeah, probably yes. Yeah.
Sorry.
Okay, so.
Can I erase it? Do you need it? Yeah.
Do you have a reason why they should be here?
Basically, I would like to define the quasi-triangular structure for the general case quasi-Hopf instead of sticking it only in Hopf algebras. That's it. Basically, I'm just using it for the quasi-triangular structure, just to see the general case, not only.
But my question is, from what you did before, it was clear why we needed the phi, why we needed the j, and why the equation were there. But here, do you have some reason why these equations?
A motivation? No, I don't have something. I just wanted to give it so that I can just give the general definition of the quasi-triangular structure. Basically, that's it. I could be restricted to quasi-bialgebras and not define that. I just thought it would be interesting to see the general definition. That's
Why this definition makes sense? Why are there examples where this appears naturally?
no, don't have something in mind. Sorry. Okay, so a quasi-triangular quasi-Hopf algebra is a pair HR where H is a quasi-Hopf algebra and there is an invertible element in S cross H and such that we have these two relations between the coproduct and R. The motivation of this, in that case, is that these two relations satisfy a quantum version of the Young-Baxter equation. The Young-Baxter equation is in braid groups. The fact that yes, this is isotopic to that you can get a strand over recrossing. And this is called the Young-Baxter equation, and there's also a formulation with vector spaces. And these two relations satisfy a quantum version that they extend the Young-Baxter equation.
So when you mean quantum, you mean just at the categorical level, or there's something more?
At the categorical level, I think, yes. And
You mentioned it at the quantum level, but I was wondering whether it just means in terms of the category of modules. That's what it is. So like what we did before, we will just translate, we view this diagram in the category of modules and translate it in terms of.
So because we understand the quantization as something like linear.
Yes, as a deformation there. So there's first the algebraic version and then the deformation. It just mean at the algebraic version. Just not the deformation.
And basically, we have the fact that the quasi-triangular structure gives us a braided monoidal structure on the categories. That was a general motivation.
So for the theorem you mentioned, you don't need to be hot, right?
No. It can be a quasi-triangular quasi-bialgebra. I just gave the general thing. We can stick to quasi-bialgebras, and I think that we can stick also to Hopf algebra. No, only quasi-bialgebras. Yes. Basically, the proposition takes H as a Hopf algebra. Okay, we have. Sorry. We let H be a Hopf algebra. And F of H is a monoidal category of H modules. Then we have that F of H is braided if and only if H admits a quasi-triangular structure. And in the case for the quasi-bialgebras, we have the one direction that if we have a quasi-triangular quasi-bialgebra, then we get a braided monoidal category. And yes. Oof. We take R as a quasi-triangular structure of H. In that case, that we have a Hopf algebra, it's just that phi is 1. So this, yes. I will write it also later, but when we have a quasi-triangular, quasi-bialgebra, then we have a braided monoidal structure, but it's only one way, not the other way around. The other way around gives us that we have a quasi-triangular Hopf algebra for sure.
You need a large diagram.
So what's your assumption? You say if you have just a quasi bialgebra, and if on that if what is a modular structure, then you're not sure whether you can find a R such that is quasi-triangular.
Yeah, okay, can you repeat? I lost.
So I said, if you have a quasi-bialgebra,
Okay,
so
yes.
just the coproduct,
Yes, quasi-bialgebra.
then you can look at its modules.
Mhm.
If you have a monoidal structure there, you're not sure whether you can.
No, that's okay. Now we're talking about braided
Yeah,
or not.
then you're not sure you can build, and if it's braided, you're not sure you can build the R.
Yes,
That's the problem.
yes,
Whereas if you start from something which is a hot,
yes, exactly.
then if you have a braiding here, you can reconstruct the R.
Yes. Sorry. I don't know. I mean, yes. I don't know if it's not possible, but I just don't know it now.
I have a question. So if this R matrix exists, is it unique? Is it unique if the center is trivial?
If the R matrix is unique, if the center is trivial.
No, is the quantum flux the only
Is there?
quantum flux like the only condition of R, or how many choices do you have for R?
I don't know, but I would. Yes, I think that it would be unique.
If you have something, something that conduces everything, you can multiply R by
Doesn't- Yeah, I don't know.
Let me ask one thing. Instead of going through the solution right now, can we just clean the blackboard and put all the things we discussed?
Just summarize a little bit.
Yeah, and maybe put some arrows to see what this.
Okay. Yeah.
Blackboard.
Yeah.
Third blackboard. Third blackboard.
Okay. So. Okay, at first, we had the quasi-bialgebras. We defined the quasi-bialgebras. And these give a monoidal structure in the category. And we also saw that it goes also back. That if we have a monoidal structure, then we can get a quasi-bialgebra. Yes, but when I say monoidal, I mean weak, not restricted to the strict case.
But so on if you call the bialgebra A, it's on the A mode.
Yes. Okay. Yeah. Sorry.
And this goes down to bialgebra symmetry.
Yes. And this is because that element phi is 1, so that means that the associator is basically the identity. It doesn't change anything, really. And okay, now if we have a quasi-triangular Hopf, then we get a braided monoidal structure. Yeah, and back, if we have a...
So on the left, this is the R, right? It was the R, and on the right is the beta.
Yes, but basically I say that if we have a quasi-triangular Hopf algebra A, the A mode category is braided monoidal. Yes. If so, R corresponds to beta, basically. We can define the one from each other. Specifically,
So the R matrix is the beta.
yes, it corresponds to beta. Basically, if in the proof we will have something like where sigma is just so beta is defined VR in that case. And if we have the quasi-triangular quasi-Hopf, then you get a braided monoidal structure, but it's not sure for the Hopf, quasi-triangular, quasi-Hopf. Oh no, quasi-bialgebra, sorry. So in that case, we get the braided monoidal structure, but not the other way around.
No, just in one direction.
Yeah.
So this is, I mean, this was the motivation of the whole thing.
Right, and then the quasi-triangular quasi-Hopf.
Well, that's the second line actually, right? When you write here, when you write Hopf, you mean quasi-Hopf, right?
Here,
Yeah.
no,
No?
I mean Hopf.
Then I don't get it.
Well,
Basically, sorry, I didn't hear.
so if you have a quasi-triangular Hopf algebra, then you get a monoidal category that you associate.
It's a straight
monoidal
non-symmetric.
structure.
It's a straight braided non-symmetric.
Yes.
Yes, it is symmetric if it's triangular.
Yeah, but there's also another one which where you have quasi-Hopf where the braid
Monoidal.
where it's non-straight.
Yeah.
Right?
Right. So
Yes.
with quasi brackets on the left, you put brackets on the right. Quasi, yeah.
Yes, sorry. Okay. In general, the motivation is that these categories can also be extended more if you want. If you have the notion of a dual object, then you can define invariants of nodes and links and three manifolds. Because if you have a dual, let's say for every V you have a V prime, then you can define two maps from the unit to V dual and from V dual to the unit. And in that case, if you have a braid diagram, you can use those maps to, let's say, somehow close it. And this makes an auto link in 3 dimensions.
Right.
Just a general motivation for if you extend it more.
I just have another question. So on the left side, we have this Hopf structure. So we have this inverse.
Yes.
And on the right, this goes. Wait. It's not clear. We are adding two structures at the same time. We're adding the triangular thing that goes to the braiding. The inverse condition, this central thing goes to the.
Yes, and I don't really know because it is not used in the proof. They just use a quasi-triangular structure.
So in one case, you only have when you have an anticode, you only have one choice of anticode, right?
Right.
I think so.
Yeah, I think
When-
check the proof.
When you have in the Hopf case, at least if you have an anticode, and that's the only possible anticode you can have. So maybe you only need the anticode like when you try to get now the listen. Yeah.
Right. Let's accept that.
No, but you have to assume that you don't get the Hofburg on the particular structure. You need to assume for the Hofburg structure on the underlying algebra A, for which you have the A mod category. And then you can go back. You don't get the Hofburg structure. Well, you don't get the existence of the Hofburg structure. You get the Hofburg structure, but you need to assume that there is one in the first place.
Yes, basically the proposition is like that if H is a Hopf algebra, we fix H to be a Hopf algebra, and we have rep H the monoidal category. Then if the monoidal category is braided, then it is quasi-triangular. It is, I mean, we take as granted that H is Hopf.
But what do you mean Hopf?
Hopf.
What's the definition of being Hopf? Because Hopf is for me, it's a bialgebra. It's not quasi. There's no quasi everywhere. Anywhere.
Yes, it's not a quasi-bialgebra. I mean, here they had two propositions. The one fixes a Hopf algebra, and it says that we get a quasi-triangular on the Hopf algebra, a structure on the Hopf algebra, if and only.
We get the braiding because for Hopf.
Yes, if and only if we have a braided monoidal category. And the second one was saying that a quasi-triangular quasi-bialgebra gives us a braided monoidal structure. Here, the Hopf algebra is fixed. It's not that they don't use it for the braided structure. They don't use at all the adipode.
And it also works if you have quasi-Hopf. That's what I was supposed to say. If you assume that you have quasi-Hopf, what you repeat, it's not works.
Yes, I think, but I'm not sure. I just gave the definition of quasi-Hopf just to see the general quasi-triangular structure. Yes, I thought it would be more interesting to see the general. Yes, I think the time has passed.
Okay.
Yes.
Maybe say 1 or 2 sentences of what would be there.
For the proof.
Only the proof.
Yes, basically that would define the braiding via R, and then I will just take these two relations, but yeah. In the Hopf algebra, if you have a Hopf algebra, you don't have the phi's, and we would see that these things correspond to the hexagon relation on the braided monoidal category. That's it, more or less.